Hello dear students and welcome back to the discussion NCERT line by line questions. Now we discuss the chapter magnetism and matter. It is a very easy chapter, okay? So we solve here 20 questions and we get the complete idea of the concepts introduced in this chapter. Okay, so the first question is the net magnetic flux through any closed surface is. The net magnetic flux through any closed surface. Okay, see, we are having the suppose a closed surface is there, suppose, and the magnetic field lines are entering into, suppose there is a bar magnet is placed, north pole, south pole, then the magnetic field lines are coming out from the north pole and these are entering into the south pole. Okay, so equal number of magnetic field lines are entering and leaving from this closed surface. Clear? Like this. Okay, in this way. So the total magnetic flux of this closed surface is equal to 0. Certain number of field lines are coming out of the closed surface and that much number is entering into the closed surface. Okay, so the total magnetic flux of any closed surface always will be 0. Simple. But this may not be the case of electric field lines or electric flux. Suppose we are having a closed surface and there is a positive charge, then the field lines are coming out of this closed surface. Then we get a positive flux. Okay, and if this charge is negative, the field lines are entering into the closed surface, then we can take it as a negative flux. This is the case of electric field lines or electric flux, but here the case is different. Okay, in a closed surface, total net flux always will be 0. The next question. The vertical plane which passes through the imaginary line joining the magnetic north and south pole is known as. The vertical imaginary plane which passes through the magnetic axis of the earth is called magnetic meridian. Okay, we studied the magnetic elements of the earth in which we have declination, inclination and horizontal intensity. Clear? Inclination and declination are angles. Okay. To define them, we should have magnetic meridian and geographic meridian. You studied it. So magnetic meridian at a place is the imaginary vertical plane passing through the place and also through the magnetic axis of the earth. So it is called magnetic meridian. Very direct question. Okay. The next one. Which of the following quantities include in the element of Earth's magnetic field? Yes. The magnetic elements of Earth are 3. Out of them 2 are angles. Inclination and declination. Okay. Inclination is also called dip angle. Okay. And the third one is the horizontal component of Earth's field. The declination. Okay. And angle of dip, it is also called inclination. Okay. And horizontal component of Earth's magnetic field. Okay. These are the 3 elements of magnetic field at any point in the Earth. Okay. So all of the above is the answer of the question. Yes. The next one. The magnetic needle shown in the figure. There is no figure. Okay, just we can imagine a figure. No need of a figure here because all the quantities are given here. Okay, we can check. The magnetic needle has a magnetic moment of 6.7 into 10 power minus 2 ampere meter square. The magnetic moment written as M is equal to 6.7 into 10 power minus 2 ampere meter square. Okay, magnetic dipole moment has SI unit of ampere meter square. Clear? Yes, we have studied the magnetic dipole moment of a current carrying loop as IA. Current into area, IA. Okay, so ampere meter square is the SI unit. Studied it. And moment of inertia of the needle is symbol as I. Moment of inertia I is equal to 7.5 into 10 to the power minus 6 kilogram meter square. Okay, yes. It performs 10 complete oscillations in 6.7 seconds. Okay, the magnetic needle oscillates 10 oscillations taking 6.7 second. Okay, then what will be the time period of the oscillation is 6.7 second divided by 10. This will be the time period of the oscillation. Yes. The magnitude of the magnetic field is, how much is the magnetic field? That is asked. Okay. The oscillation of a magnetic needle in a uniform magnetic field. We studied it as the formula as, see, time period of the oscillation is 2 pi into root of mb divided by I. 2 pi into root of I divided by mb. That's the formula, right? 2 pi into root of I divided by mb. Clear? Okay. Actually, the formula coming from torque acting on the magnetic needle is minus mp theta. Torque is moment of inertia into I alpha. Moment of inertia into alpha is d square theta by dt square. Okay. Plus mb theta is equal to 0. Dividing this with I, this is cancelled, here I comes. Okay, and now this is a second order differential equation in theta. That is the equation of a simple harmonic motion. This term mb by I is a constant and it is omega square. Okay, so we get omega square is mb by I, or omega is equal to root of mb by I. And what is omega is 2 pi by t. From that equation we get t is equal to 2 pi into root of I divided by mp. Okay, the formula is omega square is mb divided by I. From this only we are getting this formula. Time period of the oscillation of a magnetic needle in a uniform field t is equal to. Here this is omega is root of mb by I. 2 pi by t is equal to root of mb by I. Then t is equal to 2 pi into root of I divided by mp. Okay, so we can use this formula here to calculate the magnetic field intensity. Right, omega square is equal to mb divided by I. Clear? Omega square is equal to mb divided by I. Then what about the field intensity value is equal to omega square into I divided by m. Okay, we have omega is equal to 2 pi divided by time period. Clear? 2 pi divided by time period, its square, into moment of inertia divided by magnetic dipole moment. Okay, 4 pi square into I divided by t square into magnetic dipole moment. Okay, now we can put the values here. This is equal to continuation. 4 into, see, pi square we can take as 10. Approximately 10, right? 10. Okay, in calculations you can take pi square as 10. 9.9 something. Okay. Into moment of inertia value is here. Moment of inertia 7.5 into 10 power minus 6. Okay. 7.5 into 10 power minus 6. Clear? Divided by time period is 6.7 by 10. Isn't it? 6.7 divided by 10, the square. Okay, into magnetic dipole moment is, magnetic dipole moment 6.7 into 10 power minus 2. 6.7 into 10 power minus 2. Okay, yes. This is 10 square in the denominator here. It will move to the numerator here. 10, this is 10 square here, okay. The 10 square here, 10 cube. 10 cube into 10 power minus 6 is 10 power minus 3. Then this one 10 power minus 2. 10 power minus 3, 10 power minus 2, 10 power minus 2 cut. And here it is 10 power minus 1. Is that clear? Is that clear? 4 into 7.5 is 30. Okay. Okay, 10 into 10 power minus 6 is 10 power minus 5. Okay, that's fine. Here it comes 10 square to the numerator. That will be 10 square here. Okay, clear? Is that okay? Divided by 6.7 square into 6.7 is 6.7 cube. Okay, 6.7 the cube. Okay, 10 power minus 2. Clear? Now what happens? 10 power minus 5 into 10 power 2 is 10 power minus 3. Divided by 10 power minus 2 is 10 power minus 1. Okay, 10 power minus 1 into 1, 10 is here, that is 10 power minus 1 into 10, that is 1. Okay, then it becomes 3 divided by 6.7 all cube. 3 divided by 6.7 all cube. See, that will be the answer. The magnetic field intensity will be 3 divided by 6.7 all cube. Okay. For the sake of calculation, I am taking this as approximately 7. Okay. 7 into 7, 49. 49 into 7. Okay, it's around 314, that range. Okay. 3 divided by 340, in that range. You can easily check the options. Okay, 3 divided by 340, in that range. Okay, you can easily check the answer. See, 6.7, 6.7, 49, 4, 6 into 7, 42, 46, then 42, then 4, 6 into 6, 36, plus 4 is 40, okay, 9, 8, 4, 4, okay, here it comes, 44.89, okay, let it be approximately 45, okay, 45, then 6.7, okay, 35, 3, 28, plus 3, 31, 6 into 5, 30, 3, 4 into 6, 24, plus 3 is 27, okay, 5, 1, then 10, then 3, okay, then here it is, yes, 301, in that range, 301, okay, so 3 divided by 300, that will be approximately 3 divided by 300, okay, this one to the numerator, this 2 zeros means 10 raised to 2, then 10 power minus 2, that is 0.01. Is that answer? Is that given here? 0.01? Yes. 0.01 Tesla is the answer of the question. Clear? Very easy? Yes. Moving to the next one. See. Fifth one. A short bar magnet placed with its axis at 53 degree with an external field of 600 Gauss. A bar magnet is placed with its axis at 63 degree with an external field of 600 Gauss. Let this be a uniform magnetic field region. Okay. A magnetic needle is placed here. Let this be a magnetic needle. Okay. South north. Then magnetic dipole moment is directed from south to north. Magnetic dipole moment is directed from south to north, vector. Okay. The field intensity directed towards right, and the angle here theta given in the question 53 degree. Good. Okay, field value given here 600 Gauss. You know, how much is Gauss? 10 power minus 4 Tesla. 600 into 10 power minus 4 Tesla. 6 into 10 power minus 2 Tesla. Okay, this is the field strength. Clear? Yes. It experiences a torque of 0.024 Newton meter. Okay, the torque it experiences is 0.024 Newton meter. This much torque the needle experiences. Okay, magnetic moment of the magnet is how much? Magnetic moment is asked. Magnetic moment is asked. Clear? We have the equation of torque. Torque acting on the magnetic needle is mb sin theta. mb sin theta. Okay, earlier while writing the equation of SHM, I have written mb theta. Why? That is when theta is very small, sin theta is approximately theta. In that condition only, the oscillation becomes simple harmonic. Now, the formula for torque is equal to m cross b, vector m cross b, that is mb sin theta. Good. Okay, here theta given, field strength is given, torque is given. We need to calculate magnetic dipole moment, very direct question. Dipole moment m is equal to torque divided by field strength into sin theta. Okay, we place the values. M is equal to, how much is the torque? 0.024. That is equal to 2.4 into 10 power minus 2, right? 2.4 into 10 power minus 2. Yes. Divide by. Strength of the field is 6 into 10 power minus 2. 6 into 10 power minus 2. Okay. And sin theta, sin 53 degree. Sin 53 degree. How much is sin 53 degree? 4 by 5, right? Sin 53 degree is 4 by 5. Look into this triangle, whose sides are 3, 4, 5, a right angle triangle. Okay. Then the angle opposite to 3 is 37 degree. The angle opposite to 4 is 53 degree. And the angle opposite to 90, the angle opposite to 5 is 90 degree. Okay. From this, what is sin 53? This triangle, you have to learn this triangle, 3, 4, 5. The triangle of 3, 4, 5. You study like 3, 4, 5. Okay. Sin 53 is equal to 4 by 5. Sin 53 is equal to 4 by 5. Yes. Place here. 4 divided by 5. Now what it will be? 5 to the numerator. 10 power minus 2, 10 power minus 2 cancelled. 4 into 6 is 24. 24. 2.4 divided by 24 is 1 by 10. 1 by 10 is 10 power minus 1. 5 into 10 power minus 1, that is 0.5, isn't it? 0.5. Where is 0.5? Here it is, 0.5. SI unit is ampere meter square. We discussed it in the earlier question. You understood? Ampere meter square. I hope you understood it clearly. Shall we move into the next question? Okay. Number 6th. A magnetic needle is placed in an external magnetic field at an angle theta. Yes, you take this as theta. At an angle theta with the field. Needle is in most stable position if the value of theta is. If the value of theta is dash. Okay. When the magnetic needle is placed in a uniform magnetic field, it experiences torque. Tau is equal to mb sin theta. Yes. Okay. And its potential energy is minus mb cos theta. Compare this with the terms in electrostatics. In the case of electric dipole, how much is the torque is? Vector P cross vector E, that is magnitude is Pe sin theta. And what is the potential energy of the electric dipole is? Minus Pe cos theta. Here P replaced by M, that is magnetic dipole moment, and E is replaced by B. Okay, yes. Clear? And the minimum torque or the zero torque is acting when theta is 0 degree or 180 degree. Okay, torque will be 0 when theta is 0 degree or 180 degree. But potential energy will be minimum when theta is equal to 0 degree. And minimum potential energy is the most stable case. That is, the dipole is aligned in the same direction of the field. The dipole is aligned in the same direction of the field. Consider this is the dipole, south north. This is the dipole. Okay, the dipole is aligned in the same direction of the field. Okay, dipole. What is the dipole moment directed from south to north? And field also towards right. and theta is 0 degree. Now what is the torque acting on it is 0. And what is its potential energy is minus mb, the minimum value. Okay, if this is in the opposite orientation, what is theta is? Theta is the angle between field and dipole moment, that is 180. Okay, sine 180 is 0. Again torque is 0, but potential energy is maximum, minus mb cos 180. Okay, cos 180 is minus 1. Minus mb into minus 1 is mb. That is maximum potential energy, and it is the unstable case. You understood? So the answer is angle is 0 degree is our answer, not 180 degree. I think you understood it. Okay? Yes. The next one, number 6. A closely wound solenoid 80 centimeter long has 5 layers of windings of 400 turns each. Okay, there is a layer which has 400 turns, and there are such 5 layers. One layer, another layer, another one, totally 5 layers. And each layer consists of 400 turns. Okay, the diameter of solenoid is given, that is the radius is given. If it carries a current of 8 ampere, then magnitude of magnetic field intensity inside solenoid near its center is. This is a question from moving charge and magnetism. What is the field intensity due to a solenoid? The field intensity due to a solenoid is mu 0 Ni. Mu 0 Ni. Okay, if the medium inside the solenoid is vacuum, then we place here mu 0. Otherwise, if that is a ferromagnetic material, we place mu, permeability of the medium. Okay, yes. We have mu is 4 pi into 10 power minus 7. Yes, studied it. Yeah, 4 pi into 10 power minus 7. Yes. The number density. How much is the number density? Total number of turns divided by length. Isn't it? The number density. Number density is equal to, what is the number density? Number density is total number of turns divided by length. Total number of turns is 5 layers, each are having 400, means 2000 divided by 80 centimeter. Clear? Yes. This is 8 into 10 power minus 1. 10 power minus 1 to the numerator. 20 by 8. 20 by 8 is 2.5. Okay. 2.5 into 1, 2, 3. 10 power 3. Means this is 2500. 2500 per meter. Isn't it? Per meter. 2500 per meter. Per meter. That is the SI unit of number density. 2500. Good. Current passing through the solenoid is how much? 8 ampere. 8 ampere. Okay. Now, the options are in Gauss. Gauss means 10 power minus 4 Tesla. Clear? Yes. Here, you take 3 zeros or 10 power 3, multiply with this, we get 10 power minus 4. Then this will be 2.5 into 8. 2.58 into 8 is 20. 20 into 4 pi. 20 into 4 pi. Then this 10 power minus 4 Tesla. Okay. And this 10 power minus 4 Tesla we replace as Gauss. Okay. Then this one is 20 into 4 pi. Is that clear? 20 into 4 pi. But the answer is here. The answer is here. Answers. No answer suiting here. Okay. Yes. Magnetic field intensity due to a solenoid is mu 0 Ni. Fixed. Mu 0 is 4 pi into 10 power minus 7. Then 2500. The current passing is the current pipe, it carries a current of 8 ampere. Yes, it is carrying a current of 8 ampere. Clear? Into 8. Yes. Then this answer is, what the answer we are getting, we can write here. 20 into 4 pi, that is 2 into 4, 8. 80 pi Gauss. 80 pi Gauss. No such options there. Okay. This is the answer of the question as per the given data. That's all. We can change one of the options to this. That's it. Okay. Yes. Moving to the next question. Which of the following is a correct relation connecting mu r chi and mu r and chi? Mu r and chi. What is mu r? Is the relative permeability. Mu r is the relative permeability. Relative permeability. Isn't it? Relative permeability. Okay. And chi is magnetic susceptibility. Isn't it? Susceptibility. Susceptibility. And what is the relation connecting these two? So mu r is equal to 1 plus chi. We studied it. Mu r is equal to 1 plus chi. Both quantities are unitless, dimensionless. Mu r and chi both are unitless, dimensionless. And mu r is equal to 1 plus chi. The answer is option 2. Okay, good. The next one. A solenoid has a core of a magnetic material with relative permeability 500. Relative permeability, that is mu r, given here 500. Okay. Number of turns in the solenoid are 1000 per meter. Number density of the solenoid is 1000 per meter. Good. And carry a current of 5 ampere. The current carrying by the solenoid is 5 ampere. Okay. Magnetic intensity H will be. What is the equation of magnetic intensity? It is Ni. Magnetic intensity H is equal to Ni. Okay. Yes. And we studied the connection between H and M. Okay. That is M equal to chi H. Chi is the ratio of M to H, magnetization to magnetic intensity. M to H. Okay. H is equal to Ni. H is Ni. H is Ni. Clear? N is 1000. 10 power 3. Current is 500. 10 power 2. So this H value is 5 into 10 power 5. Okay. Ampere per meter is the SI unit. 5 into 10 raised to 5. Isn't it? Yes. Mu r. No. Yes. I is 5 ampere only. I is 5 ampere. Yes. No, it is okay, right? N is 10 power 3 and current is 5. 5 into 10 power 3. 5 into 10 power 3 ampere per meter is the option 1. Good. Okay. The next one. Which of the following is not a diamagnetic material? Diamagnetic material. Some materials are given here. Bismuth is diamagnetic. Copper is diamagnetic. Nitrogen at STP is diamagnetic. But sodium is paramagnetic. Sodium is paramagnetic. Yeah, it is paramagnetic. So the answer here is option 4. Okay, good. 11th, according to Curie's law for paramagnetic material, according to Curie's law, we studied the relation chi is equal to C into mu 0 by T, where C is called Curie's constant. Curie's constant. Okay. So that is Curie's law. Chi is inversely proportional to temperature. Yes. The next one. The temperature of transition from ferromagnetism to paramagnetism is called Curie's temperature. Curie's temperature is different for different materials. Okay. 13th. Suitable materials for permanent magnets should have. For permanent magnets should have very high retentivity and also very high coercivity. Okay, very high retentivity means after the external intensity is withdrawn, the material should retain a huge magnetism. The strength of retaining should be very high. That is high retentivity. And coercivity is the opposite intensity we should apply to nullify the retained magnetism. That is coercivity. We studied it. Okay. So the opposite intensity we should apply should also be very high. Then only it is nullified. Then should be it is nullified. Okay, so the coercivity should be high, retentivity should be high. That is the quality of the material of which we are selecting as a permanent magnet. High retentivity and high coercivity, option 3. Good. 14th, Curie's temperature for a cobalt is. No need of by hearting this. This is just a question. You just read it and leave it. Curie's temperature for cobalt, this is the answer, 1400 Kelvin. 1400 Kelvin, just read it and leave it. Okay, it's not going to be asked in any exam. 15th, at a certain place, a freely suspended magnetic needle makes 20 oscillations per minute. At a certain place, the magnet is 20 oscillations. Magnet is having 20 oscillations per minute. Means in 1 second, 3 oscillations. The time period is 20 divided by 60 seconds. That is 3 seconds is the time period of oscillation of the magnet. At another place where the magnetic field is 4 times. So this is T1 and there is a field intensity B1. At this region, the time period is 3 seconds. Okay, another place where the magnetic field intensity B2 is equal to 4 times of B1, the time period is, the time period of the needle will be dash. Okay, what is the equation of time period of the magnetic needle in a uniform field region? T is equal to 2 pi into root of I divided by MB. Yes, I divided by MB. We have written this earlier. Now, we understand that in this question, the magnetic needle is same. So, its moment of inertia is same. Its magnetic dipole moment is same. And we are placing this magnetic needle in 2 different fields. So, we are changing the magnetic field intensity. Accordingly, the time period is also changing. Which means that time period is proportional to 1 by root B. 1 by root B. The other quantities are constants. Okay. Then we have T2 divided by T1 will be root of B1 divided by B2 because inversely proportional to field intensity. T2 by T1, then here it will be B1 by B2. Okay, this is equal to root of B1 divided by 4 times of B1, that is 1 by 2, right? 1 by 2, yes. So T2 is equal to 1 by 2 of T1, right? T2 by T1 is 1 by 2, so T2 is equal to 1 by 2 of T1, okay. And T1 is given 3 seconds in the question, then what will be T2 half of 3 seconds, that is 1.5 seconds, clear? 1.5 seconds, very easy, yes. The next one is correct dimensional formula for the permeability of free space. What is the dimensional formula for permeability of free space? Which equation we use? We can use many equations. Okay, we have the magnetic field intensity according to Biot-Savart's law, mu 0 divided by 4 pi ideal sine theta divided by r square. One familiar equation. Okay, yes. Accordingly, the SI unit of permeability, mu naught is, accordingly, mu naught is, dB having unit Tesla. Here meter and meter square, meter is cancelled, 1 meter is cancelled here, meter. So Tesla meter, then divide by current per ampere, Tesla meter per ampere, isn't it? Tesla meter per ampere. Sin theta is not having any unit. Okay, now what is Tesla? Tesla is the SI unit of field intensity. Yes, we have F is equal to ILB. Different equations are there connecting the field intensity with other quantities. Force is I into L cross B. We studied it. Lorentz force or something. Or F is equal to Q into VB. Many equations. Then accordingly, what is field intensity is equal to force divided by current into length. Then what is the dimensional formula of field intensity? Dimensional formula of field intensity, that of force is mL T power minus 2 divided by that of current is A and L L cancel. This is mt raised to minus 2 a power minus 1. This is of Tesla. The dimensional formula of permeability is then that of Tesla is m t raised to minus 2 a raised to minus 1. Okay, and that of meter is having dimensional symbol L. Okay, and this is ampere raised to minus 1, ampere raised to minus 1, a raised to minus 1. Okay, now it will be ml t power minus 2 a power minus 2. Is that okay? ml t power minus 2 into a power minus 2. Check it. ml t power minus 2 a power minus 2. The first option itself. Understood? Okay? Very clear. The next one. Which of the following relation is correct? Symbols have their usual meaning. Okay. B is equal to mu 0, then chi, then h. These are the parameters. Okay. Yes. Suppose there is a ferromagnetic material is placed. Okay. In a field region. In a field region, a ferromagnetic material is placed. What will be the magnetic field intensity in the ferromagnetic material? B is equal to one value is B naught. That is, if this is not present here, if this material is not present here, then the value there will be B naught. Okay, and due to the presence of this ferromagnetic material, one additional quantity will be added. That is, we have written Bm. That is due to magnetization of this material. This contribution, this term is contributed due to the quality of the material. Okay, yes. And this is mu 0 into Ni, mu 0 into Ni, mu 0 into Ni, that is mu 0 into H plus. And this one is mu 0 into M. Okay, mu 0 into H plus mu 0 into M. Right. Then this is mu 0 into H plus M. Mu 0 into H plus M. Isn't it? Yes. And we have M is equal to chi H. There is a formula. M is equal to chi H. Magnetic susceptibility is the ratio of M to H. Okay. Then this one M is equal to chi H. Chi H. Then mu 0 is taken out, then H is taken out. Here it comes 1 and here it is coming chi. Okay, M is equal to chi H. H is common. Then 1 plus chi. 1 plus chi. Then mu 0 into 1 plus chi into H. This formula is true. B is equal to mu 0 into 1 plus chi into H. That is true. Okay. And what about this formula? B is equal to mu 0 mu r into H. That is also true. We have, if this is vacuum, then what it will be? The field here will be B naught only, and B naught is mu 0 H. Okay. If this is not vacuum and this is a medium of permeability mu, then what is the field? The same field we can write as B is equal to mu into H. Mu into H. This and this both are equal. Okay, and what about mu is equal to mu 0 into mu r? Then into H. Mu, what is mu? Is mu 0 into mu r. Okay, yes. And what about this formula? That is also true. B is equal to mu 0 into mu r into H. Clear? And what about this? B is equal to mu 0 into H minus m. Is that true? No. Mu 0 into H plus m. It only. So this is incorrect. Then our answer is both 1 and 2 is the answer of the question number 17, the correct formula. Clear? Okay. The next one. The phenomenon of perfect diamagnetism in superconductors is called Meissner effect. Directly we have studied it. Meissner effect. Okay. Perfect diamagnetism. Superconductors are exhibiting perfect diamagnetism. Okay, Meissner effect. Yes. 19th, a closely wound solenoid of 3000 turns and area of cross section 1.6 into 10 power minus 4. A solenoid of total number of turns 3000, cross sectional area 1.6 into 10 power minus 4 meter square, Carrying a current of 5 ampere, the solenoid is carrying 5 ampere current through it, is suspended through its center. Suspended through its center. Okay. Magnetic moment associated with the solenoid is, how much is the magnetic moment associated? See, magnetic moment associated with a single turn is IA. Yes, current into area. And here are totally n number of turns, so the total magnetic moment will be NIA. The magnetic moment of each turns will be added up vectorially. Since all the magnetic moments are in the same direction, they are simply added. IA plus IA plus IA plus IA plus IA plus equal to n into IA, n times of IA. So direct question, n is 3000, current value is 5, then area is 1.6 into 10 power minus 4. Okay. 3 zeros into 10 power minus 4, then that will be 10 power minus 1. 3 into 5, that is 15 into 1.6, then into 10 power minus 1. 15 into 1.6. Okay. 3 zeros, 10 power minus 1. 3 into 5, 15. 15 into 1.6. Yes. This one we can take as one more 10 here we are taking, then it is 10 power minus 2. 15 into 16, approximately 225 in that range. Then comparing this, I am getting this. Clear? Definitely yes. 2.4. 15 into 1.6, that will be 24 in that range. Into 10 power minus 1 is 2.4. So the answer is option 4, 2.4 ampere meter square. Good. The last question is, electromagnets are used in electric bells, okay, cranes to lift machinery, okay, loudspeaker, okay, all of the above is the answer, right? Hope you understood all the questions clearly. This is a very easy chapter. So can easily get the marks from this in any competitive examinations. Okay, study well, keep up the good work. Okay, see you next time. Thank you.